All right, everybody, let's get started. Lecture 17. I hope everybody is able to stay dry during the stormy weather. I guess we're dealing with the after effects of Hurricane Helene right now. Hurricane, right? They went from a tropical storm. Okay. Okay, so attendance grades up to date. Still working on chipping away a couple homeworks. How'd the last homework go? The moments about an accident. I will say, I do honestly believe that's the trickiest concept this whole semester. Being able to wrap your head around an axis in 3D and then another force going another way in 3D, and how much moment does that force generate around that axis. I think that's probably the most out there idea that we do today, or do in this class. Today's topic, however, I think is more about beginning the process of taking statics problems and making them much more manageable, making them easier, okay? And we're gonna start that with sort of a specific example or a specific situation, and that is dealing with force couples. And then we're gonna extend that in the next couple of lectures to a more general idea of an equivalent system. And but we'll get to that next week. Everybody get the code? Okay. All right. Okay. So just to sort of illustrate, I mean, we are still dealing with the formal definition of a moment. We are still going to be using this, but I want to maybe begin today's discussion with a little bit of math, and then tie that to something that's relevant in here, okay? So I want to begin by talking about a task which I imagine everybody in here is familiar with in math, and that's reduction, okay? And here's what I mean by that. So how many of you have had a math problem where you've been given a big old alphabet soup of variables and exponents, and then the goal is to take that and make it something a little bit more manageable? That is something that everybody in here, I imagine, has had to do, right? So for example, if I gave you a big old hullabaloo of variables, and in that hullabaloo was something like minus 4x plus 3x, you would take that and replace it with what? Negative x, right? So you would take these two terms and replace it with 1. Does that make sense? You would do the same thing if I gave you plus 5x minus 6x plus 8x. You would take all this and you say, just give me how many x, right? So what you would do is take these 5 terms and reduce them down to just 1. With me so far? You would make it more manageable, okay? The reason why that's relevant here is because we're going to be dealing with systems in this class that have oodles and oodles of forces on them. And one of our goals is to be able to take that system of forces and develop an equivalent system that has a lot less going on, okay? So just to sort of make the point on this example with the math, what would you replace this with? Zero. Nothing, right? It would cancel out, right? It would be, you replace it with 0. Okay. All right. With that in mind, I want to give you kind of the idea of what's going on with the force couple, okay? So let's just, for the sake of discussion, say that I gave you a point, a particle in space, and let's say that I put a 20 Newton force like this and a 20 Newton force like this. If you were to tell me, like, what would you replace this with? What would the equivalent system of forces be? Equilibrium. In other words, the sum of these forces is 0, right? So the equivalent system would just be this, right? So I propose that this system of forces and this system of forces are statically equivalent, right? In terms of statics, right? Now that doesn't mean, like, this point is experiencing some compression, and so maybe we would need to design for that from a stress standpoint. That's something you talk about next semester. But for the purposes of a rigid body equilibrium analysis, from a statics perspective, this system and this system are the exact same, right? So here's a system with 2 forces, here's a system with no forces. So far so good? Now, let me extend that question to the following. Let's say that I had this. Let's say 20 pounds. And let's put some dimensions on this. Let's say that this is 3 feet, 3 feet. So here I have a system of forces. Would these cancel out the same way? Like, could I take this and turn it into that? Now you're shaking your head no. Why?
So both acting counterclockwise.
They're inducing a what?
Rotation.
A rotation. This system's not wanting to rotate a thing, but this one is, right? With me so far? So what is the total amount of distance? What's the distance between these 2 lines of action? 6 feet, right? So I propose that instead of dealing with these 2 forces, I could deal with a moment, okay? And that moment would be £20 times 6 feet, the distance between them, right? And I propose that this system and this system are equivalent. You see what I did? So what I'm doing here is this system, I'm taking 2 forces, replacing it with nothing. Here I'm taking 2 forces, replacing it with a single moment. Okay? The goal is now, so here's my point. In statics, we're going to be dealing with systems that have oodles and oodles of forces in them. And I want to reduce them into a more manageable set of forces. Okay? But I'm going to begin that discussion by talking about a very specific example of multiple forces, and that is a force couple. What is a force couple? This is a force couple. Okay? So let me give you a more specific definition of what a force couple is. Okay? So let's talk about force couples. So if I have 2 forces, let's say the 2 forces here on the board or the 2 forces here on the screen, they have equal magnitude, parallel lines of action, but they point in an opposite direction. They are said to form a couple. Okay? So these 2 forces here, I have a line of action, parallel. One's pointing down, one's pointing up. They have equal magnitude. They are said to form a force couple. Okay? In other words, I can replace that force couple with a single moment. Okay? And that single moment is going to be the magnitude of that force times the distance between the lines of action. I can also use R cross F. I can do that too, and I'm going to show you that in our example today. But I can do that. That won't be an issue. Okay? Does everybody get the idea of a force couple? So again, the idea is to reduce the system. Let's take a look at this slide, because there's a lot of really good stuff here on this slide. I have a box. Okay? Bless you. I have the same box here, here, and here. What if I were to tell you that each of these systems, all 3 of them, are statically equivalent? Let me show you. Let's take a look at the first one. So I have a 20-pound couple, right? 20 pounds, separated by a distance of 6 inches. Now imagine this box was like here in the room, okay? and you took 20 pounds, pulled it this way, and I took 20 pounds, pulled it this way, we would be turning the box like this, right? We would be rotating the box in this direction, right? Now, how much would that rotation be? 20 times 6, or 120, right? What about this? Okay, well, let's say this side of the box is 4 inches, and we had a couple that was 30 pounds. What's 30 times 4? 120. What about instead of pulling and pushing on the bottom of the box, we pull and push on the top of the box? Is it the same static equivalency? Yes. 30 times 4, it's 120. So from a force perspective, these two cancel, and I'm left with just the moment. These two cancel, left with just the moment. These two cancel, left with just the moment. Same thing right here. These two cancel, left with just the moment. Does that make sense? So we can take a system of forces. So here's my point. I'm going to fast forward a little bit to show you our example. Here's our example. How many forces are on this system? I have 1, 2, 3, 4, 5, 6. This problem, I'm going to take this problem and take these 6 forces and reduce them down to one vector, okay? I'm going to make it a lot more manageable, okay? But we're going to get to that here in a bit. All right, everybody with me so far? Okay, so let's talk about a more general concept which we're going to deal with next week, which is an equivalent system. Like I said, and this is a really important concept in statics, we are rapidly approaching the idea of taking a bunch of forces and making them more manageable. So how do we do that? Well, what we're going to do is take system 1 and turn it into system 2. Now, how are we going to do that, and what makes system 2 more advantageous? System 2 is going to have less going on. It's going to have less vectors, less forces, less moments. But how do we do that? Well, I propose the following. I propose that 2 systems are statically equivalent if the sum of the forces in system 1 equals the sum of the forces in system 2, and that if the sum of the moments in system 1 equals the sum of the moments in system 2. But this shouldn't be all that crazy, because we did this with particle statics. What was the very first thing we learned how to do when we had vectors? We learned how to add them, right? So, like, here's a classical problem in this class. We have a hook. We have 3 or 4 different force vectors on them, right? What did we do? We took those 3 or 4 force vectors and we replaced them with one vector, right? And what did we call that vector? We called it the resultant, right? How did we get the resultant? We just added up the vectors. So we said, we take these 4 vectors, add them up, I can replace these 4 vectors with this one resultant vector, right? Same idea, only instead of just sum of forces equals sum of forces, it's sum of moments equals sum of moments too. We got to add that part too. We didn't have to deal with that before. Now we do, because of the propensity to induce rotation. Okay, does that make sense? That's going to be a next week challenge, but I'm introducing it because we're getting a flavor of it with force couples. Okay. So far so good? Okay, we'll have a lot of fun with this next week. Today I want to look at this, okay? So let me open up the notebook here. Okay. All right. So I have here a system shown. I've got this, like, I don't know, pyramid, prism looking thing, what have you. And I have several forces present. I have 6 forces. But does everybody notice that the forces kind of pair up, right? I've got like a 16 and a 16. I've got a P and a P, and I've got a 40 and a 40. They kind of pair up, right? So those are force couples, okay? I want to replace all 6 of these force couples with a single vector, a single moment vector, okay? And we're going to determine the magnitude and the direction of that moment vector. We haven't done that yet before, but that part should be pretty easy with what we've done so far. Okay, so far so good? Now, the goal for this problem is going to be to develop some couple vectors for these couples. So Here's ultimately what we're going to do. So I'm going to try and find the total moment on the system. And the way that I'm going to do that is this is how I'm going to write it. I'm going to write M16 plus M, and we'll call it 20, plus M40. So if you're wondering what I'm doing here, what I'm saying is that this pair of 16-pound forces causes a moment. That pair of P forces causes a moment. That pair of 40-pound forces causes a moment. So if I can write those moment vectors, I can just add them up. Okay? So that's how we're going to handle this problem. Okay? Now, before we go down the rabbit hole of doing this and writing all these vectors, I do want to go ahead and get some point coordinates because we are going to need them. Excuse me. Before we go down the rabbit hole on this, is this, I don't want to like barrel past this. Is everybody comfortable with doing this? Like taking this and saying, okay, this is the x-axis, y-axis, z-axis, being able to tell me what are the coordinates of point A. Is this something everybody's comfortable with doing? I mean, what are the coordinates of point A?
0, 0, 10, or 0, 0,
0, 0, 20. How about point B? 0, 10, 0. Okay. So I'm going to go ahead and write the rest because I'm hoping that by now this is easy. But if it's not, tell me. Bless you. Is everybody okay with these? All right. So far, so good? Okay. All right. Now, let's take each one of these one at a time, and let's see if we can work it out. Now, I propose that when dealing with force couples, there are two ways of handling it. Bless you. Two ways of handling it. There's the formal way, and then there's the observation way. Okay? I'm going to do both for this first one. So let's deal with this. Let's deal with this 16-pound force couple. So I want to focus on this and this. So let's look at method 1. By observation. And what we're doing with this method 1 is we're basically doing this. Okay, we're doing FD. So let me ask you a question. The two 16-pound forces, about which axis are they going to generate rotation? Are they going to rotate this shape about the x-axis, the y-axis, or the z-axis? The z-axis, right? Because the 16-pound force going up, this is going down, it's going to rotate it around the z-axis, right? Does everybody see that? So here's what I'm going to say. I'm going to say method 1 by observation. Okay, I'm going to say rotate about z-axis. Is that going to be positive rotation or is it going to be negative rotation? How do we figure that out? Take our thumb, point our thumb in the direction of the z-axis, and then our fingers are doing positive rotation. Is it positive or is it negative?
Negative.
Yeah, because they're rotating this way, right? They're rotating like this. My fingers have to go like that. So I'm going to say negative rotation. By the way, what is the moment arm between these two lines of action? How far is it between the two lines of action? It's 30 inches. Yeah, 30. So what I'll say is our moment arm is 30 inches. So if you want a definition for this vector, here's the vector. So FD is 16 pounds, 30 inches. 16 times 30, so 16 times 3 is 48, so times 30 is 480 inch pounds. So I propose that M16 is negative 480 K.
Is 16 on the z-axis or the y-axis? Because
Hold on. Let me write this. I think I know what you're asking. So I propose that the 16 pounds does act in the y direction. That's not what I'm asking. I'm asking about which axis are these two 16 pounds going to rotate the shape. And they are rotating it around the z-axis. Think about it like this, okay? 16 pounds, right? Imagine you're the steering wheel, right? You're turning the shape. Which axis is this?
the z.
The z-axis. That's what I'm saying. That's a very fair question, right? Does that make sense to everybody else? Oh, yes.
Can you explain the negative and positive rotation again?
Okay, so let's look at it like this. All right, hold on. Let's look at it like this. Okay, so let's look at it in 2D. So if I looked at it in 2D, would you agree that I would have that would be my couple? Okay, and so the z-axis points like this, right? Okay, now if my thumb goes like this, positive rotation is this way, but it's not rotating it that way, it's rotating it the other way. Does that make sense?
Yeah, thank you.
Now, here I want to go on to that a little bit. Let's say that for some of you, you're still having a hard time wrapping your head around it. Okay, there is an entirely another method to get this vector, and the other method is to just use a cross product. Okay, and let me show you how that works. Okay, so is everybody okay with this so far? All right, so let's look at method 2. Okay. All right. Excuse me. All right. So the way that this is going to work from a cross product perspective is we're going to take a cross product to define this moment. Now, remind me, if I have a force going directly through a point, it generates no moment, right? Right with me on that? So what I'm going to do is I'm going to consider this point right here as my focus, or my I'm going to take moments here, okay? All right? So by taking moments right there, if all I'm doing is I'm looking at the 16-pound forces, I'm going to say that this is my force vector, and this is my R vector, right? So what is R? It starts about the point which moments are taken, and it ends on the line of action, right? Now, by the way, this would also work if you took moments here and said that R goes from here to here, and I'm considering that force. So it doesn't matter. You can pick either one, okay? With me so far? Okay. So in this example, what is F going to be? It's going to be negative 16 what? You said F is pointing on the y-axis, right? So it's negative 16J. Does that make sense? Just the force vector. Don't worry about the rotations. The force is going down. That's the y-axis. So this is 16J, or negative 16J. So okay with that? All right. What about R? Okay, R is going to be the BC vector, right? From B to C, right? And so how do we do that? We take C and B. The coordinates of C are 30, 0, 0. And this is 0, 10, 0. Is that okay? Is that a fair way of doing this? Okay. So what we could do is we could say and by the way, if the cross product scares you because it seems like a lot of math, there's tons of zeros, and you'll see what I mean. We can do it this way. What are we going to get here? About here. And then negative 480 minus 0. So we can do it this way or by looking at it, and we will get the same answer. And by the way, this would also work, again, if you flipped it, right? So what I did when I summed these moments is I said, we're just going to pick one about which to sum moments. And so we'll say the force vector is the other one, and R goes from that point, bless you, to that force vector. I could have picked the bottom one and said, that's my force vector, and R goes that way to that way. I would have got the same answer. Okay? Does that make sense? All right. Any questions on that? So what I'm saying is, here's what I'm saying. So this vector is 480k. Let's see if we can do the same thing with the others. Okay? So here, let me do this. Okay. Does anybody have any questions? Yes.
Can you explain why again that's negative 16J? Because for some reason it's just not clicking for me.
Alright.
And like,
Okay. All right. So let's go back to here. Okay. All right. So I'm proposing that with this approach, with taking a cross product. Okay. All right. This is the x-axis, y-axis, z-axis. So this is positive x, positive y, positive z. If you want to take a cross product with a force couple, what you need to do is pick one as your frame of reference and look at the other one. So what I did is I chose, so I'm going to sum moments about that point. Okay? So if I'm going to sum moments about that point, this is my force vector. Okay? Now I'm saying that this vector is minus 16j. Why am I saying it's minus 16j? Because positive y goes like that. It's pointing down. So it's negative 16j because it's going down. Does that make sense?
I get that, but why is it on the Y? Because you're.
Because, right, it's going vertical.
Oh, okay, I got it now. I got it.
I'm looking at the forces. I'm not looking at the moments. I'm looking at the forces, right?
Yes.
And I'm saying that R goes from here to here. Okay? Now, the other thing I'm saying, here's the other thing I'm saying. I summed moments about point B. If you said, no, I want to sum moments about point C, then this would be your force vector, and R would go from here to here. And that would also work. You want to know why it would work? Here's why it would work. Let's say I did that backwards. Okay? What would that do to this vector?
Positive.
What would it do to this vector? It would flip the signs. So you're telling me I'm flipping the signs of this vector, and I'm flipping the signs of this vector. What's 2 times 2? What's negative 2 times negative 2? Wouldn't change anything, right? So it wouldn't matter if I did it the other way, I'd get the same answer. Does that make sense to everybody? So that part shouldn't matter. Okay. Does that part make sense? Is that clear? Okay. So let me ask you a question then. So I've given you two methods to compute a force couple. Which method do you think would be easiest to do for this pair of P forces? The first one. How about the pair of 40 pounds? I'd probably do the second one because it's at this weird angle, and instead of trying to do it in my head, let's just do R cross F. Okay? Does that make sense? So what I'm saying is for the 20-pound force vector, I'm just going to do method 1. Okay? So let's see if we can figure out what's going on with this 20-pound force vector in our heads. Okay? So let's just look at M20. And I'm going to put this on the whiteboard or the smart notebook here in a second. But let's just look at P and P. Okay? So if it's okay, I'm going to erase this because I want to make sure we're all focusing on the right thing. Okay? So we're looking at this one and this one. About which axis will this force couple cause rotation? The y-axis, right? Imagine, again, so the best way of thinking about this is imagine your hands are the P vectors on a steering wheel. Which axis is pointing towards you? The y-axis, right? Does everybody see that? So the y-axis is pointing like this. So it is causing rotation about the y-axis. Okay? Now, let's go into the helicopter. Okay? So if we're in the helicopter, bless you, if I'm in the helicopter looking down, this is the x-axis, this is the z-axis. And then I have a p vector like that, a negative p vector like that. Does everybody see that? So this is me in the helicopter looking down, so the x-axis is like that, and then the y-axis is shooting out of the board. Okay? Is this causing clockwise rotation or counterclockwise rotation? Counterclockwise. It's rotating it like that. Is that positive rotation? Yes. Does everybody see that? So we're rotating about the y-axis, and it's counterclockwise rotation, so it's positive. The force in this case is 20 pounds. What's the moment arm? What's that?
30 inch.
30 inches. So therefore, that moment is going to be 20 times 30, which is it positive or negative?
Positive.
600 what?
K.
No.
J.
About the y-axis, J. Does that make sense, everybody? So just to put that here in the notebook, so we'll say okay, let's take a step back and see how we're doing. How we're doing with the problem. By the way, let's put this up here. So this one is plus 600 J. Is this making sense? Is everybody okay with this? The funny thing is, I think the first time that you do this problem, the easiest one is these 40-pound ones. Because there's no way, I don't think, that we can easily observe the directions. So let's not even bother trying, okay? Instead, let's just use R cross F. Now, does it require more calculations? Yeah, it requires more calculations. But the upside is they're very straightforward calculations, okay? So this is how we're going to do this. So what I'm going to do is, again, so we need to, like, we can either sum moments maybe about B, and so say this is our force vector, and then R goes from here to here, or maybe some forces about here, that's our force vector, and R goes this way. We're going to get the same answer either way. It doesn't matter, okay? So I think what I did is I summed moments about here. So our R vector is going to be dB. And then our force vector is along BA. Okay? Yes?
In that case, could you also do R as dA?
Yeah, you could. Yeah, I see what you're saying. Sorry, Took me a second. That'd work too. Yeah, you could go here to here, or you could go B to E. On the flip side, you could do that too. I don't think it doesn't matter. So, but let me also say this. I think independent of each one, we just are in store for a lot of calculations, but there's no way around it. So far so good. So, okay, if that's the case, let's just start chugging this out. And if it's okay, I'm gonna try and go through some of the calculations somewhat expeditiously. So what we're gonna do for the 40-pound force couple is as follows. So we're gonna have to use R cross F. So the R vector is pretty easy, but the force vector, how are we going to do the force vector? We're going to have to get a distance vector, divide that distance vector by its own magnitude, take the magnitude, multiply, or take the unit vector, multiply it by 40 pounds to get a force vector. So we're going to have to chug some stuff out. So let's go through this. So R in this case is going to be dB. So we're going to take the B coordinate, and then the D coordinate, subtract them, no, that's inches. Now the force vector we said was along line BA. Remember that? So that came, here I'll scroll up a little bit. All right, here we said the force vector is along BA. So we're going to get BA, divide it by its own magnitude, multiply that unit vector times the magnitude. So we got a little bit of work here. So BA So BA oh, sorry. I'm getting ahead of myself. So 0I. Am I going too fast, or is everybody okay with this? Did I what? Well, it's 0 minus 10, and 20 minus 0. I got the coordinates right, didn't I? Yeah. So yeah, this is negative, that was positive. I think that's right. Okay. Now what we need is the magnitude. Sorry, the magnitude of BA. And unfortunately, this is a little bit of a mess because it's not a nice, pretty triangle. So it comes out to something like 22.361. Anybody else get that? Okay. And so lambda BA is and I'll carry that out for you. So we get 0I minus 0.447J plus 0.894K. And that's going to be unitless. And so to get our force vector, we take the magnitude. In this case, the magnitude is 40 pounds times that unit vector. And again, this is kind of messy, so and that is that. So if we wanted to determine the moment vector, we would just cross these two, and I'm just going to give you that answer. Are you okay with that, or do you want to work that out? I'm hoping by now you can do that. So it's kind of messy. It ends up being like 178.89 I plus 536.66 J plus 268.33 K. And that's a moment. So if we want to sum these vectors up, we've got this, we now have this vector. You know, just all that. So all we have to do is just add them. Am I going too fast? You tell me if I am. Am I going? Everybody good? Okay. So to keep this kind of neat, what I'll do is I'll write the M40 vector first, since it's kind of a mess. And then M20 is 600J, so it's going to be 0I plus 600J plus 0K. And then M16 is minus 480K. So what do we get? We get, here, I'll just write it like this, and then we'll go ahead and bounce because I know we're running out of time. And then this is going to be negative 211. Okay. One thing we did not have time to do here today is the problem asked us to find the magnitude and direction of this. But now that we have a single vector, we can find the magnitude pretty easily by just Pythagorean theorem. And then to define the direction, all we have to do is take this, divide it by its own magnitude to get a unit vector, and then inverse cosines to get the angles about each axis. So that part's pretty easy. So hopefully, I know that we kind of had to rush near the end, but hopefully the idea is that we can take these 6 vectors and just replace them with this, and the whole system's equivalent. Does that make sense? All right, I'm going to pull up the code one more time in case anybody missed it, but you all try and stay dry. Have a good weekend. We'll see you.